Overview of approach and methodological framework. An essential step for climate-related adaptation strategies is to estimate the risk, probability, of exceedance of critical impact levels for various impacted sectors. Such probabilities provide better insights about the likelihood that a specific climate change impact may occur, contributing to informed decisions on investments and adaptations. For this reason, we adopted a risk-based analysis framework. The premise of the study is that estimates of the plausibility of climate risks will help to develop a conceptual framework for adaptation strategies that increase the resilience and robustness of the STAP investment plan in the NRB. The adopted methodology is as follows: Gilad et al., 2013. The impacts of changes in runoff on STAP performance indicators were estimated using an existing Niger River Basin Water Resources System model, Niger Basin, by parametrically varying the hydrological conditions for the period 1966-67 to 1988-89, vulnerability analysis. The runoff elasticities of selected performance indicators. The runoff elasticity of a performance indicator, for example hydro energy production, defines the response, as a multiplier, of the indicator to changes in runoff. For example, a runoff elasticity of hydro energy of 1.2 indicates that a 10% decrease in runoff would cause a 12% decrease in generated hydro energy. Were then determined, Brown and Gridson, 2013. The runoff elasticity of a performance indicator, for example hydro energy production, defines the response, as a multiplier, of the indicator to changes in runoff. For example, a runoff elasticity of hydro energy of 1.2 indicates that a 10% decrease in runoff would cause a 12% decrease in generated hydro energy. Based on the Intergovernmental Panel on Climate Change, IPCC, A1B scenario, we estimated the probability distributions of changes in precipitation and temperature, using a bias-corrected ensemble of 38 Global Climate Model, GCM, projections of future climate for the 21st century. Using a variety of hydrologic models and methods, we determined the response of runoff to climate changes, defined as climate elasticity. Climate elasticity of runoff defines the response, as a multiplier, of runoff to changes in precipitation and temperature. For example, a precipitation elasticity of runoff of 2.5 indicates that a 10% decrease in rainfall would cause a 25% decrease in runoff. Similarly, a temperature elasticity of runoff of -0.5 indicates that an increase in temperature of 10%, for example from 26 to 28.60 C, would cause a decrease in runoff of 5% of runoff, and translated the probability distributions of future changes in precipitation and temperature into probability distributions of future mean runoff, Gridson and Brown, 2013. Climate elasticity of runoff defines the response, as a multiplier, of runoff to changes in precipitation and temperature. For example, a precipitation elasticity of runoff of 2.5 indicates that a 10% decrease in rainfall would cause a 25% decrease in runoff. Similarly, a temperature elasticity of runoff of -0.5 indicates that an increase in temperature of 10%, for example from 26 to 28.60 C, would cause a decrease in runoff of 5%. Finally, we estimated the probabilities of changes in STAP performance based on impacts of runoff changes and the assessed probability distributions of changes in runoff. In this study, climate risk is defined on the basis of changes in annual runoff as a function of projected precipitation and temperature changes. It does not take into account other sources of risk such as vulnerability of specific sectors and future socioeconomic changes, nor does it account for changes in the variability of runoff within the year. As mentioned previously, we used an ensemble of 38 climate model runs to account for model error and natural climate variability, and also to obtain the full range of possible climate futures and associated runoff. Each run was treated as equally plausible. Using these runs, the probability distributions of future runoff regimes, centered on the years 2030, 2050 and 2070 were fitted to estimate the plausibility of climate risks. To assess the severity and probability of climate-imposed risks in the basin, the generated future mean flows from the 38 climate projections were used to estimate risk levels for key performance metrics. In consultation with basin stakeholders in a CRA workshop in Ouagadougou, 2010, reductions of more than 20% from the baseline performance were considered to be significant impacts. With this guidance, We identified 5 risk levels ranging from mild risk to extreme risk, Figure 3, based on a choice of percentage shifts in performance relative to baseline operations. In this study, the baseline refers to a development scenario in which 3 dams are built, along with associated irrigation infrastructure. These dams include Fomi, Fo, in the Republic of Guinea, Teusa, Ta, in the Republic of Mali, and Kondaji, Kd, in the Republic of Niger. Thus, the baseline scenario is interchangeably referred to as the Fo-Ta-Kd scenario. We focused on 5 sectors and key performance metrics, as identified by the Ouagadougou CRA workshop participants and shown in Table 1. Risk levels based on change in vulnerability indicators. The red arrow indicates the 20% reduction in performance relative to base level beyond which impacts are considered significant. Key performance indicators and baseline values for various sectors. Climate projections typically lack credibility at the spatial and temporal scales that are relevant to water resources planning, especially in tropical regions where monsoonal systems are poorly represented and interannual variability is poorly reproduced. While a variety of downscaling approaches are available which change the resolution of climate projections, they do little to improve their credibility. In this analysis, we have attempted to address these concerns in 2 ways. First, as described above, a bottom-up, decision scaling, approach to assessing risks was adopted, Brown et al., 2012, which focuses primarily on the vulnerability of the water resources system performance to runoff changes due to climate change. As a result, the climate projections are placed in the context of risks to investments rather than as credible projections of the future. Second, the climate projections were not downscaled to higher resolution, instead, the hydrologic response of the basin was upscaled to better match the resolution at which climate projections have more credibility, i.e. at the basin scale. These approaches represent an attempt to make the best use of the highly uncertain climate information described further below. Precipitation projections for West Africa vary widely, such that GCMs even lack agreement on the direction of future changes in precipitation, figures 4 to 5. Therefore, we analyzed precipitation and temperature projections from an ensemble of 38 GCM simulations. Source: Data Library of the International Research Institute for Climate and Society, IRI. For the 21st century, to capture a quantitative global assessment of climate change-driven risks for the key metrics identified in the NRB. The projections were driven by the median A1B CO2 emission scenario, Nikitinovic and Swart, 2000. To correct for systematic biases inherent in all GCM models, we employed the quantile mapping method, as described in Wood, 2002, Wood, 2004, and Segui, 2010, and trained it on observed and simulated data for the 20th century. It was initially assessed that the estimation of climate risks over the entire NRB would be the most skillful scale for projections. This analysis was done for the periods 2016 to 2045, 2036 to 2065 and 2056 to 2085, considered representative respectively for 2030, 2050 and 2070. Source: Data Library of the International Research Institute for Climate and Society, IRI. We have also used climate change projections available for Guinea and Nigeria from the Climate Wizard website. University of Washington and the Nature Conservancy, 2009, data source: Global Climate Model, GCM, output, from the World Climate Research Programs, WCRP, Coupled Model Intercomparison Project Phase 3, CNIP 3, Multi-Model Dataset, Meal et al., 2007, was downscaled, as per Maurer et al., 2009, using the bias correction/spatial downscaling method of Wood et al. 2004, to a 0.5 degree grid, based on the 1950 to 1999 gridded observations of Adam and Lettenmeyer, 2003. ClimateWizard.org, and the WBG's Climate Change Knowledge Portal, Climate Portal, as being representative for respectively the Upper Niger Basin and the Lower Niger and Benue Basins, to determine whether climate change impacts in the Upper Niger, Guinea, and Benue, mainly Nigeria, basins could be more or less severe than the average impacts across the Niger Basin. The Upper Niger and Benue Basins constitute the main water sources, water towers, of the Niger River. Results are shown in Table 2, showing a good agreement between the various sources of climate change projections. University of Washington and the Nature Conservancy, 2009, data source, Global Climate Model, GCM, output, from the World Climate Research Programs, WCRP, Coupled Model Intercomparison Project Phase 3, CNIP 3, Multi-Model Dataset, Meal et al., 2007, was downscaled, as per Maurer et al., 2009, using the bias correction/spatial downscaling method of Wood et al. 2004, to a 0.5 degree grid, based on the 1950 to 1999 gridded observations of Adam and Lettenmeyer, 2003.